Hello everyone. In this video we are going to cover the two mechanics topic, that is work, energy and power. Now when we talk about energy, it is a scalar quantity and there is very important principle or law which follows the what we call as conservation of energy. Now conservation of energy that you might have learned earlier, it suggests that energy can't be created nor it can be destroyed. Correct? And what we need to know is it can be only transferred from one source, one kind of energy to other kind of energy. And usually there are, what we do is, if there is any kind of change in energy, so this is change in energy, or in simple term we will say mechanical energy. Change in mechanical energy will be equal to some work done plus some heat that is generated. But usually for the most of the system for this chapter, we are going to consider most of the problems Q will be equal to 0. So no heat dissipated across this will be work done. Okay. So this is what the first law of thermodynamics and usually first law of conservation of energy suggests. All we need to know is, first we need to understand what is the energy. So let's understand a concept called as work done. Now work done by a constant force is given by imagine there is a block or a toy that is like tied to a rope and a kid is pulling it horizontally. So the displacement of this toy will be d, and the force that is applied is F in this direction. Now obviously if this object has some mass attached to it, it will require some energy to pull this block to move to this position. Correct? So work done by a constant force is defined as a product, or I will say it is a force applied in the direction of displacement times distance traveled. So this will be given as work F. Now you can see that not all the work is done in the direction of displacement. So I will take the component of the work. There will be obviously two components. So this is component along the direction of the displacement. So we can write this as F cos theta times the distance traveled is d, or we can write this as Fd cos theta, where theta is the angle between force and displacement. It means that if for the forces which are vertical and the displacement is happening horizontally, the cos theta, cos 0 degrees 1. It means the force is in direction of the displacement. If the cos theta is 180 degrees, and it will be minus 1, it means the force is against the direction of the displacement, like you are moving in a certain direction and you apply a brake, so the friction force is backwards and the car is moving forward, and if the cos theta is, let's say, 90 degrees, if the force is acting vertically, well, but the displacement is happening horizontally, in that case that force is not doing any work because cos 90 is 0. That's the reason why even the centripetal force or magnetic force does not do any work because they are perpendicular to the displacement. Okay. Now this is work done by a constant force. Another example of this leads to something that is called as gravitational potential energy. Now what is potential energy? Potential energy is the energy of the system or object due to its state or position, okay, of the matter. Now gravitational potential energy is basically nothing but work done by gravity, work done by gravitational force. Now you can see that if there is an object, let's say it is at this place at rest, okay, and it is at a height h. So here the force is mg, that is the weight. Now this force is responsible for this block to fall through this distance and reach its final place, that is ground. So what you will see is that the force and the displacement are in same direction. The work done by the gravity will be nothing but the weight times the height, that is the displacement that is happening. So usually we write this gravitational potential energy to be equal to mg, that is weight, into h. Now important thing is, what if, like, this is the hill road and a ball is about to roll down this hill and there is some height h2 here and some height h1 here, okay, and this object will come from this height to this height. So what will be the change in gravitational potential energy? The change in gravitational potential energy will be mg h2 minus mg h1, and that will give me mg h2 minus h1, that is mg delta h. So you can see that the gravitational potential energy does not depend on the path. The Gp does not depend on the path. It only depends on the initial and final vertical position. Depend on initial and final vertical positions. So that's very important. So no, regardless of what path it takes to reach that point, it is only depending upon the height. Now another thing we need to notice about is another kind of energy is something that we call as kinetic energy. Now kinetic energy, you can write this as Ek, is due to a motion of a particle, correct? So whenever a particle moves, it will have a kinetic energy that is given by half mv square. Now before we move on, just let me just quickly write what is the unit of this work done. The unit is of any kind of energy is basically joules. We write it as G. Now kinetic energy is half mv square, and because of it is motion, So if the object is at rest, let's say here it is at rest, and here it is moving with velocity v, it will have a kinetic energy half mv square. So let this A to B. Now from A to B, what you will see is that according to conservation of energy, if this surface is like frictionless, like no energy is lost to anything, then the energy at A will be converted to what the energy at B is. Okay, so this two quantities will be absolutely equal. So energy can't be lost anywhere. So energy at A will be mgh2, while energy at B is both things. It will have kinetic energy plus potential energy. So mgh1 plus half mv square. So you will see that if I take this term here, I will get this term half mv square. I can cancel out the m and I can get v in terms of 2 square root of 2g delta h. So this is how we can relate both of this quantity depending on the height. So what we can say is that the gravitational potential energy, whatever the change in gravitational potential energy is happening, is converted to kinetic energy. Okay. Now, now there is one more kind of, what if the force is not constant? So if the force is not constant, then in that case, what we do usually, so for example, if they have given you a force which varies with the distance traveled or displacement, force that varies with displacement. In that case, what we do is, like, if the graph is like this, the area under the graph, the area under the curve represents work done. And this is very useful because we can find the area of different kind of graphs and we can get how much work is done. A, a great example of this is elastic potential energy. So let's take a quick example of what we have learned in Hooke's law. So this is mass m, if it is k, and if this is an equilibrium position, and if I pull this mass to the right, and if I make a displacement x from the equilibrium, the block will experience a force towards an equilibrium, and that, according to Hooke's law, under elastic limit, the spring force will be equal and opposite, okay, and to a displacement, and it will be related to this quantity, that is k. Now where k is something that we call as spring constant. So it means that here display x is a displacement, or we can say it is the extension in the spring, and spring constant is given by this. Now what if I need to find how much is work is done by the spring? So in that case, if I plot this graph, if this negative sign just represents the direction, it does not contribute in magnitude. So this graph will be a straight line if I plot f spring versus x. And area of this graph from 0 to x will give me work done. So what will be the area? If this is x, then this point will represent here kx because spring is this. So if I take the area, it will be half, area is half into length is x, and the height is kx. So what I will get, work done by the spring is half kx square, and this is something that we call as elastic potential energy. But one more thing that we need to remember about this phenomenon, just imagine this spring is already away from the equilibrium. It has some extension x1. Now somebody pulled this even more, creating an overall extension of x2. So how much energy or how much work done to move the block from x1 to x2? So in that case, again, we will see the graph of spring and displacement. This graph will be straight line. On this graph, you will see that there are 2 points, like let's say x1 and x2, which are related to k x1, and this will be k x2. So just work done from x1 to x2 will represent, give me this area. Okay. So this area of this trapezium can be found by taking the area of bigger triangle and subtracting it from smaller triangle. Okay. So work done will be, the bigger triangle will be half k x2 square, and the smaller triangle will be half k x1 square. So work done will be half k, I can take common, x2 square minus x1 square. You can see how this is how we can relate different quantities. Okay, and we can get elastic potential energy when the force is not constant but it varies with respect to displacement. Now there is important concept of conservation of energy, but most of the time we get confused when to apply and how to apply conservation of energy. So I will give you a concept where conservation of energy will always hold true or help you. Now there are two kinds of forces. One are conservative forces and other are non-conservative forces. Now what are those non-conservative forces? Now those non-conservative forces, or sometimes I also call it resistive forces. Examples of this conservative forces like gravity, electromagnetic forces, elastic force, okay, or spring force. So these are the forces for which the energy is conserved. It means that the total change in energy is zero. It means the initial energy will be equal to final energy, and the kinetic energy, initial energy, is a sum of kinetic energy and potential energy. So I can write Ek initial plus Ek EP, that is potential energy final, is Ek final minus Ek, sorry, plus. Okay, so this is true for all those forces because they conserve energy, they are path independent, and you can directly use initial energy and final energy. It is up to you. You can choose any 2 points as initial and final, and you will get a relationship between those equations. Now, the resistive forces includes something like friction, drag, air resistance. Now, those kind of forces which opposes the motion, they, for them the energy is not conserved, and the change in energy will be always be equal to some work done. Now this is very special. This is a work done by a resistive force, and this is change in energy. So change in energy can be also be written as final. Now, since the resistive force acts in the opposite direction of the motion, the initial energy is lost. The initial energy is lost to the like some there will be some final energy and there will be some work done. So I can remember this change in energy to be equal to EF minus EI. Now this work done will give me this. And most of the time this work done is negative because the force is resistive, so force is in opposite direction of the displacement. I can give you an example about this. So imagine there is a car that is moving with a velocity v. Now this car comes to rest after applying some brake. So this car comes to rest applying the brake. So final velocity is zero. Okay, final velocity is zero. Initial v. Now what caused this car to stop? At this position, the car was experiencing a backward friction force while the car was moving in this direction. The friction force F, which depends on coefficient of friction and the normal. So if this car has some weight m, then the mg will be balanced by the normal force, and we can write this as mu mg. Now what is the energy change here? Initially it has some energy half m u square, while finally mechanical energy will be zero because it has zero velocity and it is also on the ground. So the change in energy is obviously not conserved. The change in energy will be work done by the friction force. So some energy that we see is all converted into friction. So half mu square minus 0 will be work done by friction. The friction will be mgh. So let's say this car has traveled distance some d. So we can calculate this d by using this relationship. Okay, so this will be half mu square is equal to mu mg into d. So even if we don't know the mass, it's completely fine. We can find d is equal to u square by 2 mu g. This. So these are the this is how we use conservation in case of non-conservative or resistive forces are applied. Okay, and the last concept in this particular is the power. Power has multiple definitions. It is sometimes also referred to as rate of change of energy. Okay, and it is measured in the unit is watts. So the main definition of power is change in energy over time. So you can take energy between any 2 points and how much time it has taken. You can use this formula. And most of the time, this formula students forget. Students just remember this as energy over time. It is rather change in energy over time. So if I am taking energy versus time diagram, if I take a gradient of this, then I will get a power. Okay, so that is a constant power. Now most of the time we will have given some examples where power is equal to some change in energy is also some work done over time. And for a constant force, this is very important. For a constant force, the force is just constant. I can use work done as force into distance traveled over time. and force over distance traveled over time is nothing but into velocity. Now this equation is applicable in few conditions that we need to remember. First, imagine a situation where a car is having a forward force of engine, but it is exactly balanced with the ba- backward force of friction so that the car is moving with a constant velocity. So the net force here is zero, correct? But if I want to calculate what is the power for the engine, then I can use F engine into V. So in this case, the forward force of engine is constant. It is not the velocity is changing. Okay, so it is moving with a constant velocity. There's a constant force, constant velocity. Then we can figure out the power. Okay, so everything is constant in this case. Then we can use this. What if it is not constant? Then if V is not constant, or even the force is not constant, then what we are getting is an instantaneous power, which is given by F into V. But at that instant, what is the velocity and what is that force that we need to get? If V is not common, but it is, we know that what is, if we know initial and final velocities of the motion, we can figure out the power that is we called as average power, which will be equal to force, that is average force times average velocity. Now, average velocity we have seen in kinematics, it is given by initial plus 1 upon 2. So this is something that we need to remember when we know this. Okay. Now we should be able to relate power with something that we call as efficiency. Efficiency can be defined as useful power output upon power input times 100%. So usually we can calculate, so most of the time they will give you efficiency. You can calculate output or input depending on what they have given. Okay, in that situation. So there is one more thing that they ask sometimes is the graph of power versus time for a constant force. So for this, we know that for a constant force, mass is constant, acceleration is constant. Okay, and usually the velocity, if it is starting from rest, it is given by u plus at. So I can write v is equal to at if it is starting from rest. So power is equal to F into V. So F I can write as ma, it is a constant, and velocity I can write it as a t. Okay. So what happens is like this velocity, the power will be continuously changing with time. Okay. So this is how we can relate all those quantities. Okay. In that case, so whenever they give you ask you a graph of power versus time or anything, you just relate the quantity. Like for example, if they ask you what is the form relationship between kinetic energy and the time, so we know that V is equal to U plus AT, but if it is starting from rest, it will be just AT, and then kinetic energy will be half. Instead of mv square, it will be a square t square. So if I plot a graph of p versus t, it will be like a curve upward. So we need to look at those five from small equation, and we can calculate all those. But most important thing to remember is that when to apply it. So if I read a question, I particularly see whether there are resistive forces or not. And if there are no resistive forces, I can use conservation of energy directly. If there are resistive forces, then I have to use change in energy should be equal to the work done by the resistive force, which can be written in some cases FD. Okay, so this is what we have covered so far in this particular chapter. Thank you so much.